Now we will talk about the modeling of synchronous generator. However, in detail modeling course is not done here in this chapter, so but it will just give a brief overview of how you can come to like an equivalent diagram that we will use in our calculations. So here you can see a sketch or 2D sketch of how you can represent build up your model of a synchronous generator. So representing a stator and a rotor. You can see some axes here. We have one A axis, one B, and one C axis. They are of course then 120 degrees separated. And then we have two other axes that I just mentioned earlier, is that we have a D axis and a Q axis. They are locked to the rotor, as you can see here. The Q axis is then 90 degrees behind the D axis in this feature here. So, and you also can see an angle here, theta. Here's theta R, but in the book is theta D is used. And it indicates the position of the field winding, and the D axis are relative to the A phase. When we do some modeling, we do some simplifications, and you can see one thing is that the MMF in the air gap is distributed sinusoidally, and the harmonics are neglected. Secondly, the saliency is restricted to the rotor, the effect of slots in the stator is neglected, and thirdly, the magnetic saturation hysteresis are ignored for now. And also you can see some windings here. You can see on the Q axis we have 2 windings, and on the D axis we have two windings. If you look at the D winding, we have then a voltage source. So this is the field winding representation, and then we have a winding for damper bars on the D axis. The same for the Q axis, we have 2 damper bars. And depending on what kind of topology we have on the rotor and what kind of transient behavior we want to analyze, we can neglect one of them, or we can neglect 2 of them, and we can get different types of models. So for example, for the salient pole rotor, we can have what we call a 2.1 modeling, and that's a possibility. We of course also have the windings for the A axis, for the B axis, and C, which is the 3-phase windings. Here is the feature from the book, somehow similar, it's a little bit different in notation here. But you have the A, the B, and the C axis, and we have the field winding. And as you see, it's representing then the D axis, is following the D axis. So this is an idealized 3-phased generator showing identical armature coils and field coil. The direct axis leads the quadrature axis by 90 degrees in the counterclockwise direction of rotation. The modeling part is a little bit simplified in this lecture compared to a full-blown model. But the idea is very good, and we can look at it. Of course, this is a self-inductance we have. This is something you have seen on the transformer. So we can represent one LS for the LAA, LVB, LCC, self-inductances. And then we can, for the mutual, we often use the MS here, representing the mutual inductances. Then we can combine all the flux linkages, as you can see here, for the A phase. We also have for B and C, I just show the A phase, where we have the current IA, IB, IC, and the field current. We can further then do some simplification. So we can, as I said above, we now have the LS current IA by introducing the LS here. And we also can introduce the MS, the mutual, representing here, and of course the field. In addition, we can use Kirchhoff law, and we can do this relationship, insert that. And then we can get for the A phase flux linkage, the LS plus MS times IA plus LAF times IF. So as you can see now, it has two flux linkage components, one following the current A, the stator current, and the field current. Now we also have introduced the mutual for field winding between A and F, and the capital current IF, now with a cos 2 omega t plus theta d0. Now, as we remember from the transformer, using the Faraday's law, we can introduce this flux linkage into this equation. And we have this relationship here. So the last term of the previous equation can be represented an internal EMF, which we can call now EA dashed. This EMF can be written in this fashion, where the RMS magnitude, as you can see here, is proportional to the field current and is defined in this fashion. The action of the field current causes a EA dash to appear across the terminals for the A phase when current IA is 0, and is called by various names such as the no-load voltage and the open circuit voltage, the synchronous internal voltage, or the generated EMF of phase A. So different names on this. You will probably see that in the literature also. The angle theta d0, as I already shown, indicates the position of the field winding relative to the A phase at t equals 0. That's why it's written in this case. So it indicates the position of the q-axis, which is 90 degrees behind the d-axis. For later convenience, we need to set the theta d0 delta plus 90, and then we have, as you can see here, where theta d, omega, and delta have consistent units of angular measurement. So this delta, as you can see here, we often can also say it's a rotor angle. So here is the figure 330 in the book, and now we can come to this armature equivalent circuit. So now we can see on the EA dashed phase, the A phase here, and the B and the C. So as we know, we can now just take per phase of this three-phase system and start to analyze. So now we'll go further on this analyze on the equivalent diagram, and we look at the synchronous generator versus a power line. So to the left here on the A, this is a cosinusoidal representation, as we just saw. However, we will work with the phasor representation, as you can see here in the B. And then we have the generated at no load, the internal voltage here, and we have a resistor. And I have an inductance that both is the mutual and the self-inductance combined. So this is simplified greatly. And then we have the external voltage on the terminals and the currents flowing. So this is typically represented as, because this is a power, so it's delivering power to the grid. That's why we had this minus on the voltage on the last equation, as you previously said. So for the phasor representation, you can see down here the all components together. So we have the voltage A on the terminals is equal then the internal voltage times the minus the voltage drop, the resistance, the voltage drop due to self-reactance, and voltage drop due to armature mutual reactance. So this is what we call the armature reaction. And it means that when you're putting up a field in the rotor, it actually provides a counteracting field in the stator, and this interaction is what we call an armature reaction. So this is impedance. We can then write set impedance D for actually that we are in this fashion, R plus J XD, where the XD represent then both the self and mutual reactance. We can actually now look at this comparison with the synchronous generator versus a power line. So above here you can see then the internal voltage E and the XD as just said, and the resistance of the armature, and the current and the voltage. Of course, we have a turbine connected to the generator with a torque of Tm, with a speed, synchronous speed, omega s, and so this is the mechanical torque, this is the electrical torque on the generator side. For the power line, we typically can represent it as a sending end voltage and a receiving end voltage. And then we have a reactance of the line and a resistance of the line. And we can also actually take it one step further, where we have a lossless synchronous generator per phase equivalent, as you see here. And now the resistance is removed. And the same, we can also model the power line in the same fashion, where we just neglect the resistance. Typically, the reactance is much larger, much greater than the resistance for both of the components. Now we can develop the simple two-port equations for such a two-bus power network, which also can be done with a round-rotor generator. So up here we have the phasor diagram E equal U plus JXI, as you can see here. So E is the sum of U vector plus imaginary value of XI here, complex value here. So we can say that the E with the angle delta, so you have here, equal U with the angle 0 plus this vector. Then we also have this phi, the angle between voltage and current. And we will also find this up here. We can see that down here in this drawing that we have the phi here. So we can then divide in the real and imaginary part. So if you look at the real part, then we have E cos delta. That means actually the vector coming from here and all the way here, or maybe you can see here from this part. That means it's U plus xi sinus to phi here. And the same for the imaginary part, which is this, is actually xy cos phi. Why is d here is just related to the generator, where you can represent the xd instead of the x. So we can then rearrange the equations and get that the current times the sine to phi is E divided by x cosine to delta minus U divided by x. And the same we can do for the I cosine to phi. So now we have we know that the complex power is U times current complex conjugate, and we can then insert for I cosine to phi this expression, and for I sinus to phi this expression, and we will get this relationship I see here. This is very famous for the power and the reactive power for such a two-bus power network. And as you see from the generator, we had the same diagram, but now the only thing is that we have this synchronous reactance XD representation, and the one important to say is the delta, where we have transmission line angle separation, and it equals then the rotor angle.